All right, I guess we can start. So, hi everyone, and thanks for joining us today. I hope you all had a great week. Today we have the pleasure to host Patrick, who is a PhD student at the University of Tübingen, and he will be sharing with us some thoughts on identifiable, exchangeable mechanism for causal structure and representation learning. So before handing the mic to you, Patrick, let me remind you all of some house rules. As usual, clarification questions will be allowed to be asked during the talk. For people in person, you just have to raise your hand and wait for me to give you the mic so that people online can hear you. And for people online, so we don't have the sound directly coming in, so you'll just have to type your question online. I'll be monitoring the chat and read out your question when the time is right. There'll also be some additional time at the end of the talk for people to ask further questions, make some comments, or have a more informal discussion with Patrick. That's pretty much it for me. So whenever you're ready, Patrick, floor is yours.
Great, thank you so much, Rim. And I would also like to thank Victoria, who helped me pull this talk together. And thank you so much for coming. As Rim mentioned, I'm a PhD student in Tübingen, and we work at the Max Planck Institute for Intelligent Systems, and I'm a fourth-year PhD student. And in this talk, I will share with you our thoughts about how we can find and unify the common themes in identifiable representation learning and causal structure learning. This project is joint work with Siyuan, Ferenc, Huszar, Bernhard, Scholkopf, and Wieland, Brendel. So the main focus of my research is representation learning, and there usually what I want to achieve is to learn a useful representation, whatever useful means. Of course, like the usual pipeline is that we feed a data set into a neural network to get a latent representation, and then what we want to get with this latent representation is to solve some sort of downstream task, or in the case of causal inference, we want to discover causal effect relationships. And of course, the big question what interests me and what is the focus of this talk, whether we can provide theoretical guarantees to show when and how we can get to something useful in the end. And there are multiple approaches to characterize these theoretical guarantees. The first one is identifiability, which you can think of as having a parameter family, basically just a neural network, and you train it multiple times with multiple different seeds. And identifiability tells you that the latent representation given by one neural network and the other relate by some trivial transformation to the ground truth representation, whatever the ground truth is. And of course, that also means that they relate to each other by, let's say, scalings or permutations. On the other hand, causality has a very useful conceptual tool, which is called Peir's causal ladder, after Julia Peir's groundbreaking work. But maybe let's just first one other key for the identifiability part. Then you can think of it as high level, as like you get identifiability as the interaction of constraints on your data distribution or latent distribution and the function class. So yeah, as I mentioned, in causality, Peir's causal ladder is a useful abstraction. And there you can think as having a data generation process where you have beyond the equation some sort of graph as well. And otherwise, your pipeline is quite similar that you feed a neural network with data and you want to infer the latent representations. And here you can have different granularities. So round one is when you only get statistical associations. This is most of the machine learning and deep learning toolkit. If you go one rung above, this is the interventional ladder, when you can also infer the graph and make or like answer interventional questions. That is what would happen if you would change a specific variable. And the top of first causal ladder is the counterfactual one, which includes learning these functional maps from your latent variables to the observed causal variables. And in this case, so both approaches are about trying to guarantee recovering some sort of structure or representation. But then you can ask whether they are related. And in the linear case, we already know this since a while, that they are related. And for this, I will illustrate how they relate with an algorithm called Lingam, which is a linear non-Gaussian additive noise model method, which uses independent component analysis from the identifiable representation learning literature to learn the representation, and also it uses ICA to discover the causal graph. So here we assume that we have a data generating process with the graph depicted on the slide. And here you see that you have a triangular structure in your data generative process, but this doesn't really tell you about the graph, because as you see here, there you have many more non-zero items than the edges. But if you invert it, which you can do by ICA if you have non-Gaussian noise variables, then an interesting structure emerges. Here you see that the only non-zero elements which are not on the main diagonal actually depict the causal structure. So you can use this inverse map to do causal discovery, basically. And then the question is, which I tackled during my research, is investigating whether this is true in the nonlinear case. People were thinking that, yeah, it seems reasonable, but it was not shown formally. And basically, I was able to answer in the affirmative, where you can do this whole process of feeding data coming from a causal model into a neural network, which I call here an inference model, which inverts this data generation process, and then you get the inferred latent variables. And if this method, which inverts the data generation process, is an ICA or like an identifiable method, where you have specific identifiability guarantees on your latent representation, then if you calculate the Jacobian matrix of this inference model, it also has the same structure. So the Jacobian, also in the nonlinear case, encodes the causal structure. And of course, you can say that, well, this is not surprising. And this is also what the reviewer said, because what does the Jacobian contain? It's just partial derivatives. And if there is, if a variable affects another one, then if you would change that variable, that is, if you would calculate the partial derivative, then you expect something like a non-zero number. And basically, this is what we have shown, that here, like doing ICA still helps you recover the causal structure. So this was another point to show that there is a deep connection between identifiable causal structure learning and identifiable representation learning. And another point where these methods or like fields seem to connect is the answer of the question, what makes identifiability possible? Of course, there are many different approaches. Here I will focus mostly on the multi-environmental setting. And in this case, ICA usually posits some sort of variability condition, which basically means that if you have data coming from an environment one according to a specific distribution, then you need another environment which has a different distribution. In the causal case, you usually start from observational data because this is the cheapest, but then you need to have access to interventions, which you could also model that if you intervene on causal model, then you expect having some different distribution. So basically, in the end, these are kind of the same. And you can say that, okay, actually what we need is non-IID data. And the answer which leads to this unifying perspective we are exploring in our work is actually this non-IIDness, how we can characterize this non-IIDness. And so how there is also like a fundamental conceptual difference how ICA and causality looks at the data, or like what it assumes about the data. So in ICA you have you always start from the point that you have the data which satisfies your assumptions. You don't know and don't care about how you got there. You just assume that you have this, let's say, multi-environmental data, and then you feed it into a neural network, and then you got an identifiable representation. So this is what I tend to call the passive view, because you don't, like, the data is given, you don't do anything with the data in sense of data collection. On the other hand, what causality does, especially since it has notions such as interventions, there is like an active interaction, let's say, with the environment. You can think of it as like an agent, even like a reinforcement learning agent, which moves around the world and tries to collect data. And I term this an active view. But in the end, actually, and this is what I tried to show in the previous slide, the characterization of the data, what you need for identifiability, is kind of the same. So the question is whether there is a formal notion which encompasses both of these paradigms. And for this, in our paper, we answer with the notion of exchangeability. Basically, what exchangeability means that if you have multiple environments, then you can think of these environments as having parameters, and each environment's parameters are sampled from a parameter prior. So basically here on this graph, you can think of these XY pairs as being in different environments, and the environment parameters theta and psi, they need to be a have a non-delta parameter prior. So to compare this to the IID case where we know that identifiability is not possible, then if you would start from the same graph, then we need to cancel out these parameters, because there is no distribution. It's just a delta, so it's always the same. So basically, exchangeable data is a mixture of IID data sets, where for each environment you have an IID data set, but across environments you have different mixture components. And it was shown by Siyuan previously in her causal definitive paper that exchangeability leads to non-IIDness in your data, which enables causal discovery. And basically, this was the key component where we started to build up this unifying perspective, because exchangeability, turns out, can describe these variability conditions in ICA across multiple environments, and also in the causal literature where the variability conditions emerge from interventions. So yeah, this was kind of a long introduction. So let's now dig deep into what the identifiable exchangeable mechanisms framework does, or what it aims to do. So basically, in IEM, we are modeling all types of different variables people are interested in identifying. So we have 3 levels. We have the source variables. This is what usually ICA is interested about. And these are, in most cases, independent source components, which in the case of causal models are mapped by a structural equation model. So basically, this is the causal lower triangular structured set of equations I showed you on previous slides. And after the mapping with the structural equation model, you get the causal variables, the relationship between which is encoded in a directed acyclic graph. But of course, in the real world, you don't observe these types of variables, so you need to also model some sort of high-dimensional mixing, which in the end leads to observed variables. So if you only take away one thing from this talk, then let it be this, that the difference between the types of causal discovery, identifiable representation learning, and causal representation learning methods we are trying to unify here is basically only what components in these models are modeled, or what are observed, and what is the target quantity. So to turn this kind of simplified graph into an ugly figure. I will show you this multiple times and hope that this is not very confusing. It basically expands the same graphical structure I showed you when explaining exchangeability, but it's a bit expanded to be able to encompass all three paradigms. So here, the difference is that on your left-hand side, in these big nodes, I'm modeling the causal structure, basically. So that's kind of the structural equation model with the sources and the causal variables. And the parameters, again, are denoting that you have parameter priors such that in different environments, let there be observational or interventional, your data distribution is different. And I will also use color coding to make it a bit easier to parse. So blue will be the target quantity, which is basically what the specific method is trying to infer. Then red will denote the things we assume to be observed. And if there is any such thing, then I will gray out the components which are not modeled. So this is the high-level IAM framework. But now probably you are interested in that, okay, what can we do with this? Because this seems like some sort of arbitrary bunch of graphs, and you can't really tell now whether it's useful. So let me try to convince you that it's actually useful. In the first part, I will focus on causal discovery. And to see the relationship, I will start from the causal definite theorem, which shows that from exchangeable data, in either the bivariate or the multivariate case, you can do causal discovery. So basically what the causal definity theorem says that if you have a joint distribution over XY pairs, then you can factorize it in such a way that the cause and the mechanism have independent parameters. So basically you can think of the causal definity theorem, which was Siyuan's previous work, as turning the independent causal mechanisms principle in causality, which says that the components of a causal model neither inform nor influence each other. So they are in some way independent, but this is not statistical independence in the ICM principle. It turns it into statistical independence of the parameters when you factorize the joint. But yeah, basically instead of the integral, you can think of it that here there is like a component of the cause distribution and one about the mechanism distribution. And again, the key takeaway is that these mechanisms have independent, like in this case, statistically independent parameters. So this theorem relates to different notions of independence, basically. So how this relates to the IAM principle, and I will do this slide magic to turn this ugly figure into something slightly more simple. So in causal discovery, you don't model the source variables. This is why they are grayed out, and I already omitted the observations because you don't have high dimensional observations. In causal discovery, you always assume that you observe the causal variables. And what you are interested in is, and I hope you can see it, that the arrows between the Zs are blue. Basically, you're interested only in the graph. So, okay, we can fit causal discovery into the IAM framework, but then so what? Actually, IAM also shows you how you can relax the conditions of the causal definite theorem. So as a reminder, basically, this is the exchangeable setting in the bivariate case what the causal definite theorem talks about, that you need a non-delta parameter prior for both variables to be able to do causal discovery. But actually what we show in our paper that's sufficient, it's not necessary, because you can do something as what we termed cause variability, when only the cause variable has a non-delta parameter prior distribution, or by symmetric reasoning, you can do the same with the effects mechanism. And what we show in our paper is basically that these two components in the bivariate case are the necessary and sufficient conditions to be able to do bivariate causal discovery, which fits nicely into the view that we do know that IID causal discovery is impossible in this bivariate case. And we know that the other end of the spectrum is the fully exchangeable setting. And basically, causal mechanism variability is the in-between. And it turns out that the in-between is actually enough to identify the causal structure. So this is about causal discovery. And now let's go into identifiable representation learning. So in recent nonlinear ICA methods, at least in some of them, what you do assume is that you have conditionally independent source variables. And then basically this will be the key how it fits into the IAM framework, because you can think of the conditionally independent variables, how they vary across environments as exchangeability. And this is what is usually described in algebraic variability conditions, that what they usually say is that, okay, apart from maybe ruling out specific distributions, you need to be able to distinguish the distributions across environments. And of course, in ICA usually assumes that your mixing function is deterministic. And if this is the case, then we can turn this general IEM graph into something like this. When we don't have the causal variables, so I omitted the Z and also the graphs from these nodes on your left. And of course, we are interested in the source variables, the latents. And what we observe is the observed variables. So again, yeah, ICA fits into the IEM framework, but then what do we gain from it? And what we gain from it is actually a nice dual view on the identifiability results. And we motivate this with the example of time contrastive learning, which is one type of multi-environment nonlinear ICA method, where what you assume is that you have non-stationary sources across the different environments. You can think of it as, for example, the fMRI recordings of different patients. But the mixing function is deterministic. So with a slight twist of the graph from the previous slide, I can also show this with this other graph where I only have a parameter prior on the source variables, but none on the observations. And if you think that, well, this is actually very similar to the causal variability setting I showed you when talking about the relaxation of the causal definity theorem, exactly that's the case. And you can do the other way around. And this is what we showed, that if you have stationary sources, but your mixing is stochastic, of course, in a specific way, then you can get this mechanism variability akin to the to that case in causal discovery, and that's still sufficient to identify the representation. And so, and why this could be interesting is that in most nonlinear ICA methods, the mixing function is assumed to be deterministic and the same across environments, but there are not many methods which explore a stochastic mixing function. The only one which is slightly related, but the exact relationship is still unclear to us, is the incomplete Rosetta Stone paper by Luigi Cresela. So there, I would expect that maybe there are other new identifiability proofs if this dual approach is taken. So this was the representation learning part and how it fits into IAM. Now let's go to causal representation learning. And for this, I will use the recently proposed causal component analysis by Van Dong et al. To show how causal representation learning, or at least a subset of causal representation learning, because causal component analysis is like a bit simplified compared to general causal representation learning. Nonetheless, I think this is an instructive example to show how causal representation learning can fit into this framework. So what causal component analysis does, and yeah, the naming is definitely intentional to be similar to ICA, is that it assumes that you observe high-dimensional mixtures, and you also assume that the graph is known. So basically, this is the difference from general CRL, that you make your life easier by assuming that the graph is known. But here you also assume the access to diverse interventional data sets. So this is the kind of the multi-environmental aspect of causal component analysis. So with these descriptions, basically the IEM graph turns into something like this, where you don't explicitly model the source variables. You do have high-level observations, but what you're interested in is basically the causal variable level. So yeah, in this case, I don't have new results, but what I can show you at last is maybe some ideas what could be the IM framework's potential, besides what I talked about previously, because in most of these methods, so causal discovery, identifiable representation learning, and causal representation learning, they are focusing on identifying a particular aspect in this model. But sometimes maybe you want to identify multiple levels, maybe simultaneously. And there is actually a paper proposed recently, which is called Identifiable Latent Neural Causal Models by Liu et al., which proposes something actually quite similar, where they're trying to identify both, or they're not trying, they are identifying both the source variables and the causal variables, but they do it in like a two-step process, and what they assume is basically very similar to what I have talked about previously, namely that you have high-dimensional observations. They put a restriction on the causal level, namely that they assume that the structural equation model, basically the mapping between the Z variables, is an additive noise model. And they also assume that they have access to diverse data from different environments, but they do it for two levels, both for the source variables, because basically what they use is TCL, so traditional nonlinear RCA. But to be able to identify the causal structure, they also need to assume this variability for the causal level. And here, one question what I'm quite interested in is that, okay, you have two variability conditions, but obviously since this is one model where the source variables affect also the causal variables, maybe you could relax these conditions into one particular condition on maybe a new type of variability. Because so what we can already show, and this is how we applied IEM on this framework by Liu et al. to try to say something new, is that if you apply basically the causal definite lens on these different parameters of the components of the IEM model, then because you have an additive noise model where the source variables are kind of separate in the structural equation model, they will have statistically independent parameters. So, and this is kind of purely speculation. You can think of it that if you have variability in your source variables, then since the source variables affect the causal variables, there might be a notion of variability on the source level, which actually gives you the required variability on the causal level, thus basically throwing away one set of assumptions, which could make these sometimes pretty strict assumptions in the identifiability literature maybe a bit more realistic. To conclude my talk, basically what we did with the IEM framework is provided kind of a unifying lens with the notion of exchangeability on particular causal discovery methods, identifiable representation learning methods, focusing mostly on independent component analysis, and also causal representation learning. What I must say is that IEM is not universal. As I try to emphasize, this is mostly about the multi-environmental setting. So if you are interested in a more comprehensive unifying framework which focuses only on CRL, then I highly suggest you check out Yao et al.'s paper, which was, I think, put on archive like 2 weeks before, so like right on time that I can say this. It's called Unifying Causal Representation Learning with the Invariance Principle. And she works with Francesco Locatello at ISA in Vienna. And I highly recommend that paper. So with this IEM framework, what we did, we relaxed conditions on the causal definite theorem, so provided a more general set to identify the causal graph in the causal discovery setting, and also suggested new identifiability results for source and causal variables. I think that there is still a lot to explore in this field, especially that these different notions of non-IID data, people tend to characterize them differently, and we try to summarize this also in the paper. But it's unclear what is the sufficient and necessary set of variability, because most of these proofs provide sufficient conditions. And in the causal discovery setting, you are able to provide the sufficient and necessary conditions. But of course, there is a lot more work to do. But I hope that with this framework, I provided some inspiration. And now you are thinking that, well, these are interesting questions. I should do research on this. And then I would be happy that I reached my goal. So I would like to thank for your attention, and thank all my collaborators, because without them, this project couldn't have happened. And if, in case you have any questions, I'm happy to answer those. And you can find the preprint there at that QR code. Thank you.
We have some time for questions, if there are some.
I have a question.
You start us off with just a small one that's clarification about your earlier work. Could you go back to the slide on the Jacobian causal discovery? I was just curious how that differs from the identifiability results for nonlinear additive noise models.
Okay, so here I think it's a different means to the same end.
Okay.
And one more thing, maybe that here we don't need to assume that it's additive.
Yes, that's what I wondered. Okay.
Guessing as an intervention. Like guessing on stationarity somewhere.
Yeah, I don't think I have a clear answer for that, because of the kind of different, like, ICA doesn't talk about interventions. This is what I try to highlight in the active-passive view. So basically what this proof requires is that you do ICA and have strong identifiability. Then you can do this already. And of course, ICA doesn't assume having access to interventions, but under the hood, I think that it basically does something like that. For example, in contrastive learning, when you have these paired views, then the augmentations, you could argue, and I would totally agree, that those are interventions. Mm-hmm. So as an ICU person, I would say, no, these are not interventions, because the ICA literature doesn't talk about interventions. As a causal person, I would say, yes, sure, ICA just doesn't call it that. So yeah, I think that there is no, like, definitely there is no free lunch there. It's just, so you need some sort of signal, and this signal is actually, multi-environmental data, which you can interpret as being a consequence of interventions.
So this required multi-environment data. Okay.
Yes.
That's probably a big difference as well, because the really original additive nonlinear models result was just observational data. The asymmetry came from
true.
Okay,
I should have said that.
Okay.
Thanks. I have a very basic question. So when you talk about IID and exchangeability, can you go to that? Yeah, so I have problem just understanding so if you have if you assume exchangeability, by definition, you have a latent variable model, and then you can assume samples generated from that model are IID.
So could you please speak up a bit?
So when we talk about exchangeability of set of variables, by definition, means you have a latent variable model, basically, right? Which means you can think about these as being IID samples from that latent variable model. So what is the difference? I think I'm missing your key point in this slide. And which
Okay,
a
so
lot of argument depends on.
okay, so your question is about what is the key difference between the IID and the non-IID setting, right?
Yeah, so you were distinguishing these two. You were saying exchangeability, I'm dealing with multiple environments and I'm going to use that, but you can also think about that as IID being samples that are IID from a latent variable model, right? Or is there something more?
Okay, so exchange, like if you have exchangeable data, then a single environment, like samples in a single environment are IID. And you can think of basically, if you frame exchangeable data as a mixture of IID, and basically the mixture is regulated by the latent variable.
Right, yeah, okay.
Does that help?
Yeah.
Okay.
So I thought I missed something, but
Right, thanks.
I guess my question is about causal definity. So I think you have like the integral somewhere. This one, yeah. So for me, it sounds almost like an assumption. Like, what's the theorem? What's the statement of the theorem?
Okay, so but causal definity shows that so the original definity theorem shows that if you have exchangeable data, then you can model the exchangeable data as a mixture of IID data where each mixture component has independent parameters. And the difference from that, so basically the original definity theorem compared to that here, I wouldn't have py given x and px, but it would be just pyx given, let's say, theta integrated over the parameter prior. So basically, what the causal definity theorem says is that if you have exchangeable data from a bivariate causal model, then there are parameters with which you can factorize your joint distribution in this way. And then basically, how causal definity operationalizes this principle is that it leverages this independence of the parameters and carries out independence tests to check whether you have found those parameters. Because if you are able to find such parameters, then that also means that you found the causal factorization.
So maybe just I think there should be like a p theta p phi in the integral. No, like there's no distribute. There should be like a prior there.
Yes. Yeah. Sorry. Yeah. Thanks.
I guess more questions will come later.
I have two questions online. The first one from Alexander, who's asking in practical terms, how many environments do we need to effectively use IEM for causal discovery?
It depends. Yeah, that's I don't think I can provide a general answer.
Okay.
I mean, in the bivariate case, okay, yeah. So I don't know whether I want to go down the rabbit hole. Here, the clear distinction between theory and practice is that most of these theoretical results showing the required number of environments is not considering, let's say, practical aspects such as how ill-conditioned the problem becomes. So in a very quick summary, when you do nonlinear ICA, for example, or other methods relying on such variability conditions, you need to invert matrix. And then if that matrix is non-singular up to an epsilon, you can invert that matrix. But of course, in practice, if the condition number is big, then you are having trouble. So this is why there is no single answer, because if you have a very limited amount of environments, but their variability is different in air quotes, that would mean that you don't need as many because your problem is better conditioned. If you happen to be unlucky and your environments are very, very similar and your matrix is ill conditioned, then that means that you probably need to collect much more data to get to a stable solution from a numerical point of view. I know that this is not a real answer to the question, but this is the best I can do now.
So I think it's linked to Joshua's question, who's asking, in the real world, we will never get a complete coverage of all possible interventions, even in an asymptotic sense, because some interventions are not physically or practically possible. Shouldn't we start exploring those cases, which fell outside of the framework of identifiability and require maybe something like Bayesian posteriors over graphs and parameters?
Okay, so let me try to rephrase whether I understand the question. So basically the question is about that there are a lot of interventions which are not feasible. So in practice, right? And that could limit the practical applicability. And thus that maybe we could use a different framework, let's say a Bayesian framework, to mitigate these issues. Well, I think it's a very valid point, and actually I have a project upcoming which is quite related to that. So I don't want to spoil that. Okay, I will. And yeah, this will be a bit tangential, nonetheless. In the case of theoretical results, of course, we also, or like in a lot of the cases, we want good generalization, not just in distribution, but out of distribution. And for this, recently explored notion is compositional generalization. And there, of course, you can get quite nice guarantees on generalizing OOD on product spaces. But of course, there might be some combinations in the product space which are not feasible. So basically what we are trying to explore, and this is really at an early stage of a new project, that you can think of the relationship between compositional generalization and counterfactuals as being related by a Bayesian prior, where basically the counterfactuals or the causal view capture all our prior knowledge of the world, and it rules out some of the combinations that the compositional sense would admit. So basically, this is kind of me answering in a very long way, saying that, yeah, I definitely think that the Bayesian view has merit, and I also think that identifiability has some shortcomings. For example, within an equivalence class, it doesn't account for the fact that different, from a probabilistic point, equivalent models have different probabilities of being picked up by network during training. So I do think that identifiability needs an extension which should be Bayesian at least to some extent, potentially accounting for these differences within the equivalence class. And for the particular case of OOD generalization of large language models, I have a paper together with Ferenc, Huszar, and his students at ICML, where basically that's what we are trying to explore, how these differences arise and how the Bayesian perspective could be useful for OOD generalization theory for LLMs, and of course how that could inspire practical use cases. So yeah, this is already like a very long answer. I hope that this answers the question to some extent.
Thanks.
It's about like the causal definity thing again. So like the original theorem was, I think, was about like infinite sequences of exchangeable, like infinite exchangeable sequences. And there's not, I don't think there is a finite version. So I'm just wondering what the exchangeable data is here, because you seem to be like, dealing with, at least in the diagram, like pairs of like things, right?
Yes, so basically your question is about the infinite sample versus finite sample discrepancy. In practice, you wouldn't have infinite samples, right?
Right, but I guess the exchangeability comes in from like, I guess, different multi-environment setup here, right?
Yes.
So unless you have infinite numbers of environments, I'm wondering how it's, I don't know, if there's a deeper connection to the original Di-Finetti's theorem that I'm missing.
Okay. Yeah, I would be happy if Siyuan would be here now. Probably she can answer that, but I will try to make an attempt to. Yeah, you are right that the formulation is about infinitely exchangeable sequences. But then, if I remember correctly, then the paper has also kind of a, maybe I would call it reformulation, where for a specific n, you have exchangeability of that sequence of length n. And that, yeah, that n can be a natural number, so I don't know how much it helps. That's a fair point that ICA theory is basically all, with one exception I know of, assumes access to infinite data. So
Yeah, but infinite data is not the same as like infinite environments of.
oh, sorry, so the environments don't need to be infinite. Within an environment, your sequence length, or like the number of sequences.
But don't
Can
you
be-
assume that within an environment, your data is IID as opposed to, well, I mean, it is exchangeable. Like, it's exchangeable because it's IID within an environment.
It's exchangeable because it's IID given an environment, yes.
Like, okay, maybe I've understood this wrong, but my understanding was that because you have multiple environments and each, like the data from each environment is IID, by like doing all this stuff, you can decompose it into like different, like a mixture of different environments, right? Or no?
So if I understand you correctly, yes. So if you pick an environment, all the samples that come from that given environment, those will be IID. If you pick a different environment, those will be IID for that environment, but these two won't be IID.
Okay.
Okay.
Yeah.
Did I answer the question?
Yeah, I think so.
Okay, sorry.
Any other question?
So I think just after causal definity, you had the result for identifiability of the graph, like causal structure learning. Yeah, this one. I think like there was already a literature on like, given a subset of interventions, what can you identify? Like what will be the equivalence class given that set of interventions? Like which arrows are you going to be able to orient? And here you sort of have, I guess, a different version of that result. I'm just trying to understand like how does it fit with the result that were already known in that space. Because for instance, this this was already known, right? Like that if you have intervention on the cause, you can identify. Same thing for the effect, right?
Yes. I think that's a fair point. Yeah, I think we didn't explore this connection back to interventional results because, at least in my interpretation, the notion of exchangeability is more tied to like non-interventional settings.
Not only.
I mean, like
more
you
general.
can. What I'm saying is that you can model some interventions as exchangeable. I think that exchangeability was not invented to model interventions. So yeah, I think this what you're saying. Yeah, this is basically describing known results from a different perspective.
Okay, thanks.
Any other question? All right.
The neural SEM work that you started talking about, I don't know if you could go to that slide. Am I right in understanding that maybe one reason we would want to identify the source variables themselves might be for the sake of inferring counterfactuals?
Yes.
Okay. I also, this is just a maybe philosophical point more than anything, but I find this idea of getting interventional data about the source variables kind of interesting and weird because I can totally understand maybe the distribution of the exogenous variables is non-stationary or something like that. But certainly them being exogenous kind of suggests we can't intervene on them. I think that's kind of pedantic though, because really I think what you mean here is that there's some variability, not that the variability comes from humans intervening.
I mean, I think that's a fair point. I was also thinking about this, and okay, what if we identify like multiple levels, like whether that really gives us anything in practice? I mean, I agree with you that for counterfactuals that would be probably useful, but yeah, sometimes I was having trouble in thinking that, okay, what would be the exogenous variable and how could we modify that, or how could we intervene on that, or like even if we can't intervene, how can we observe such settings where we have a reasonable chance that they differ. So yeah, I think that it remains to be seen for like a particular example, because thinking about it like theoretically, I'm missing the grounding into the real world to see that, okay, maybe this makes sense in this case, but not in that.
All right, so I think we can officially end the talk and thank Patrick again.
Thanks.